Okay, picking up where we left off, let's just go back to a general form of a solution that we had for this discriminant being negative case. What we saw is that a general solution to our differential equation could look just like so. Now, we considered what could happen if our two constants were both 1. That's where we left off with the first video. What if we chose our first constant to be a 1 and our second constant to be negative 1? If we did, what we really would wind up with is factoring out e to the alpha x. We'd have e to the beta ix minus e to the opposite beta ix. Well, you might remember where we left off before too, is we considered what e to the beta ix minus e to the opposite beta ix was. Shockingly, there was an imaginary component in there. And you could see that it's 2I sine of beta x. Now immediately this can be a little disconcerting, because very naturally students are going to look at this and say, now wait just a minute. You're saying that this solution has an imaginary component to it. What we're saying though is that when we substitute that in, the left-hand side of that differential equation will equal 0. Dare I say, to help you out with something, please remember something that I hope is pretty obvious to you, that 0i would be equivalent to 0. So guys, wonderfully, we could also say that e to the alpha x times 2 sine of beta x would also be a solution, and you could confirm that. Well, what we're really seeing right now is these two quantities right here, and forgive me, I think I left off a 2 for that, the addition term. You could see that we'd have e to the alpha x times 2 cosine beta x was a solution. E to the alpha x times sine of beta x with a 2 out in front would work as well. Well, hey, how about we realize that the 2's are just constants in and of themselves? You could show that a more general solution would be this right here. If you're ever worried about showing that those are linearly independent solutions, you could even use the Wronskian that we learned earlier in the unit to confirm that. But that would be a general solution when we have the imaginary discriminant. Well, let's take a real close look as to what's going to happen here. If we were to substitute in y equals e to the mx, and that would lead to y prime being m e to the mx, and y double prime equaling m squared e to the mx. And if we substituted those values in, and if we were to divide by e to the mx, very quickly we would arrive at this wonderfully simple quadratic equation. Quadratics can always be solved via the quadratic formula, but probably the first ways that you've learned to solve quadratic equations would involve factoring. Set these factors equal to 0. Very quickly you would arrive at m equals 4, m equals 1. This was our first case, and you could call this m1 and m2. Amazingly, this m is e to the mx. It's the number multiplied to x. So we could say y equals c1 e to the 4x plus c2 e to the 1x. Wow. We're done. Take a look at our next problem right here. Working this out very quickly in a similar fashion. If we were to very quickly again say y equaled e to the mx, y prime would be m e to the mx, and so forth. You could see, once again, you arrive at a very simple quadratic. The big difference here is that you will have repeated factors. You get m is equal to 7 when you set m minus 7 equal to 0. And this right here would yield the discriminant equaling 0. Take a moment just to go back to case 2. You could see if we had e to the m1x as a solution, the other solution would be x times e to the m1x. Wow. Very, very quickly, we arrive at a general solution of c1 e to the 7x plus c2 x e to the 7x. And we are done. Finally, as we look at this last component, making a similar substitution, of course, we would arrive at a quadratic once again. Now, I must state that this is all coming from y equals e to the mx. With this quadratic, we could divide by 3. But you'll quickly notice this will not factor. And that then begs the question, how on earth would we solve? Well, you could actually hit C-solve on a TI-89, or we could use the quadratic formula. Now, the quadratic formula would be a nice simple way to do this by hand. You can see that A would equal 1, B would equal -4, C would equal 13. And as we simplify that, we would get the opposite of -4 plus or minus the square root of -4 squared, which becomes a 16. 4 times 1 times 13, all over a 2. So this becomes 4 plus, well, that's 16 minus, what is that, 52, I believe. And 16 minus 52, if I'm not mistaken, is 36, or -36, I should say. But the square root of -36 is 6i. Hey, divide by 2, and you'd get 2 plus or minus 3i. This is your alpha. This is your beta. So I could say alpha is equal to 2. Beta is equal to 3. Well, we just saw a moment ago at the very bottom of that, well, I should say more towards the bottom of that second page of notes, the general solution, once you know what alpha and beta are, my goodness, once again, you can get a solution very, very, very quickly. What would that final solution look like in a general form? Y equals e to the 2x. In here we'd have c1 cosine of 3x plus c2 sine of 3x. And that's it. So again, this is always assuming that we have constants in our linear homogeneous differential equations. And if we do, we can use these little guidelines that we talked about today. Well, good luck to you. The homework is going to more or less always yield these quadratics. Best of luck.